Here we're going to have our first names, and then the variable 2, we'll use the other variable last names. And we can go up to 10 there. So 5 and 5. All right, so these are the people who have joined us online. There may have been a couple more that have joined since, but we'll just go around the class. Just give me 2 numbers first, and the number of letters in your first name first, number of letters in your last name second, and then we'll fill out the scatter plot. So we'll start here.
6 and 10.
6 and 10. All right, and we'll go here.
10 and 4.
10 and 4. And over here.
6 and 11.
6 and 11. So you had to throw that 11 at me. Back in the back.
6 and 7.
6 and 7.
7 and 8.
6 and 7. 7 and 8. And right there.
5 and 7.
5 and 7. And right here.
6 and 9.
6 and 9. And 6 and 8. All right. And it's pretty easy, guys. You know, again, I mentioned last week that we have a bit of an algebra background needed for this class. Well, what we do when we create our scatter plot, we're essentially creating coordinate pairs. All right. So we're going to plot this 5, 7 on our scatter plot. All right. The first name response, that first person had 5 letters, and then their last name, they had 7 letters. So that dot represents the 0.57 in our, if we thought about this as an X and Y in our coordinate plane. And we move down the list, 8, 5. That's approximately 8, and that's approximately 5. That would be the 0.85. On our scatter plot, we wouldn't necessarily list those points, but I'm just trying to explain how this is done. 6 and 5. So here is our 6, and up here is our 5, 6 and 5, and then so on and so forth. 6, 10, 6, 10, and 10, 4, good buddy, 10, 4. My dad had a CB radio when I was growing up in his little truck. It was pretty fun. 6, 11, 6, 11, 6, 7, 6, 7, and 7, 8, 6, 7, 8, 5, 7, 5, 7. There's another dot there, and 6 and 9 and 6 and 8. 6 and 9, 6 and 8. All right, and that would be our scatter plot. All right, doesn't mean anything to us just yet if we're looking at it, but that's really all we have to do in order to create one. Do we have any questions on how I created that scatter plot? Points in the coordinate plane, plotting points, right? All right, X and Y axis. All right. Once we have a scatter plot, we'd like to be able to describe what we're looking at. We'd like to say, oh, here's a scatter plot. Let's tell our friends at the party, what does a scatter plot look like? And there are 3 things used to describe. Often these things get confused with how we describe histograms. They're a little bit different. With a scatter plot, sure that's on there. With a scatter, okay, we can do this. With a scatter plot, we're going to describe its direction, its form, and its strength. All right. Now our options for direction are going to be positive or negative. There is a third option, which would state that it had no direction. All right. When we think about direction in terms of a slope of a line, all right, we try to you know, if you have a line y equals mx plus b, then we know the slope is m. If the slope is negative, or it has a negative sign in front of it, then it's a negative slope, and negative slopes move like this. And if that value of m is positive, it's a positive slope, and positive slopes move like this, as values of x are increasing, y's are decreasing for negative slopes, as values of x are increasing, y's are increasing for positive slopes. If something is, you know, kind of like this, then we would say it has no slope. What we want to do is we kind of want to visualize what's happening to these lines. Do we have any noticeable trend? Are we moving from the upper portion, the upper left side, to the downward right? Or might we be moving from the downward left side to the upper right, right? If the lines have a trend that is moving in that direction, we would call it positive. And if these dots rather have a trend that is moving in this direction, we would call it negative. And it's kind of subjective because it might be hard to read from time to time. But generally, I would say that in this particular case, we probably have more of a negative direction. Dots are kind of moving in this fashion, as you know, it's very slight, if at all, but I would see kind of a general trend slightly down in that direction. So a possibly negative direction for this particular example. All right, possibly negative. For our example, but what would a positive direction look like? Well, a positive direction again would have dots that kind of move in that general direction like this. We can notice this upward trend for the positive slope. Something that had no direction would be all over the place. It would be a little bit chaotic. You wouldn't really be able to tell what's going on. It would look like a cloud of dots. All right, something like that. All right, so be able to look at the dots and express some sort of direction, whether it be positive, whether it be very easily to see negative, not as easy to see negative, or no general direction. The next thing we need to describe is its form. And options here would be linear. It might be exponential. It might be logarithmic. It might be, what's another type of equation you would see in algebra? What's the parabola? Quadratic? It might be quadratic. Or we might have no form, all right? All of these are curves in algebra. So generally, at least in this class, we're going to have, we could break these down into one category. We could say either this form of our scatter plot is going to be linear, meaning our dots move in a progressive line-like fashion, which this might be the case. That would be a particularly linear negative scatter plot. Or it could be curved. Maybe something like this is happening. We start negative and then we turn around and become a positive. That would be a curved. Or we could have a form that really has no linear or curvature to it. It could be mass chaos, in which case we would have no form. Right? If we get into the habit of no direction and no form, we have no association. Right? If I'm looking at this particular thing, I would say generally it would be linear. An argument can be made for a slight curve that happens right there. But I would say generally in this particular example here in the class, we would have a linear form. I'm going to stop and pause for a moment and say 99% of the time in this class, we will have linear forms. Because if we get into a curve situation, we really can't do any analysis with that in this class. That's for a higher level statistics class. But if we have a linear form that is positive or negative, that becomes a positive or negative linear association. There is a lot of analysis that can be done with that. All right, so linear is fun. Everything else a little bit boring. We'll throw it out. Okay, any questions on direction or form? I mentioned a lot of statistics are subjective. And that's where that's kind of the problem we run into when we talk about strength. Right? Is our association strong? Is it weak? Is there none? Is it something in between strong or weak? How can we describe the strength of its association? Well, visually, The strength of an association has to do with how close the dots are to a line. How close dots fit on one line. All right. The more we can draw a single line through all of our dots, the stronger our association. For example, and I want to make sure I can move the computer just a little bit so those of you online can see. If I had a scatter plot that looked like this, all right, I can pretty much draw a single line through all of those points. All right, and that would be almost a perfect association, a perfect line. And we would call that direction positive. We would call the form linear, and it's very strong because I can draw one line through all those points. As I move to maybe a second example where I have something like this, all right, now clearly I cannot draw a single line through all those points, but I can draw a line through most of those points. So this is still very strong, not as strong as this because I encompass less dots, but still very, very, very strong. If I move down to something like this, of course, I'm going to get weaker and weaker. All right. Then we have a much weaker relationship. We might consider this somewhat strong because, the general trend is apparent. But again, this would be a positive, somewhat strong association. We can still draw a line through a lot of dots, just not all of them. And then as we get more into the chaotic sense, we get a very weak association going on like there, right there where, what line is going through all those dots? Is the line coming this way? Is the line coming this way? What's going on there? Do we have an S curve? I don't know. All right. So the more compact we are to one line, the stronger this relationship is going to be. And even if we had, something like this, even if we had more dots closer together, that would even impact the strength and make it stronger. All right. So it gets to be a little bit subjective, but if we can understand the idea of being close together on one line, being stronger, then we could probably make an estimate as to the relativity of strength or weakness. Okay. Direction, form, and strength. If we're looking at my example here, I would say that this is a negative linear association that is moderately strong, somewhat weak, somewhere in there. Okay. Any questions so far? Nothing? All right. We can get a little more precise, though. We can get a little more precise with relating strength through the correlation coefficient. So I'm going to introduce coefficient. I'm going to introduce a new statistical value. This value is R. Anytime you see R, little r in statistics, we're talking about the correlation coefficient. And R specifically measures the strength of an association. Right, specifically measures the strength of an association. R is always going to be a value between -1 and +1. All right. It can equal +1. It can equal -1. But more often than not, it's going to be between -1 and +1. If we have a negative correlation coefficient, that's going to tell us the direction. It's going to tell us that we have a negative direction. If we have a positive correlation coefficient, that means our association has a positive direction. And the closer that we are to 1, the stronger the association. Anything that has a perfect -1 or a perfect +1 is a perfect association. This would be the strength of this measured in the correlation coefficient because I can draw one line and connect all the dots, and we have a positive form here. the correlation coefficient here is probably 1.0. If we did the same, moving in a straight line toward a negative form like this, this would be an R value of negative 1. Those of you who can't see on the screen, I will move that way. Here we have a positive direction. The strength of this, if we were to estimate the value of R, the correlation coefficient, okay, R is going to be positive again. It's not going to be 1 because it's not a perfect one. We have these outliers here, but it's still going to be pretty high. I would say it's somewhere in 9, or excuse me, between 0.9 and 1. And then we would get even weaker here. R here might be around 7. It's still clearly positive, but there's not a line that can connect most of those dots. And down here, R would be very close to 0. Anything that's close to 0 is saying there's very little association going on there. All right. So the next question would be, how do we calculate R? How would we calculate R? All right. All right, R is equal to the summation of Zx times Zy all over n minus 1. So let's break down what all of these values mean. We've run into this before. Summation means we're adding something together. And in this case, we're adding a whole bunch of products. The product of this times this, divided by a number of entries minus 1. All right, in our particular case here, the value of n was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n minus 1 would have been 10 in our example here. But what does Zx and Zy mean? What do you think? What would Zx and Zy represent? Where have we seen a Z before? Very recently. These are Z-scores. All right, so these represent standardized scores. Now, I'm not going to move through and calculate this correlation coefficient for you, but I will try to show you how it's actually calculated. What we do is we standardize all of our values here. We try to find the average number of letters in our first name. So if we look here, we have what? 13, 19, 25, 35, 41, 47, 54, 59, 65, 71 divided by 11. 71 divided by 11, 6, remainder 5, 0, that's going to be 4, remainder 6, 0, that's going to be 5, roughly 6.45 is going to be the average, okay? Roughly 6.5, maybe, let's see, 5, maybe right about there, right? If we were standardizing then that means that if that's the mean, then that standardized scores would be 0. And if I wish I had a red marker with me today, that would be amazing. But if I were to, let me get rid of this blue to help it make more sense. If I were to divide, make sure that these are okay. Divide this, mark the center of this as a left and right half, then everything over here is going to have a negative z-score, right? And everything over here is going to have a positive z-score. Does that make sense? All right, the average is always going to have a z-score of 0. So everything or every letter number to the left of 6.45 will have a negative z-score, and every first name with a letter count higher than 6.45 is going to have a positive z-score. Similarly, I can do the same thing with last name. This brown is not going to show up. Have I done this before? It might. I can do last name. That's 17, 27, 31, 42, 49, 57, 64, 73, 81. 81 divided by 11. 11 goes there. That's 7 times remainder 4, 0. So that's 3 times remainder 7, 0. That's 6 times. 7.36. 7.36. That might be a little high. 7.36. Yeah, that looks good. And I would say, all right, let's create a hash through there. This would have a z-score of 0. And when we're dealing with last names, any last name that had fewer than 7.36 letters would be a negative z-score, and any last name that had higher than 7.36 letters would be a positive z-score. All right. Now, each of these points represents an x-coordinate and a y-coordinate, and as we transfer these x coordinates to z-scores, they become a zx. And as I transfer the y-coordinates to z-scores, they become a zy. So essentially, I'm multiplying together z-scores, all right? A z-score for x and a z-score for y. A z-score for 5 and a z-score for 7, I multiply them together. Now, if I multiply a z-score for 5, which is negative, and a z-score for 7, which is negative, I'm going to get a z-score that is, or excuse me, I'm going to get a product that is positive or negative. The z-score of 5 is negative, and the z-score of 7 is negative, then their product is going to be positive or negative. Positive, right? Because a negative times a negative is a positive. So anything that exists, any dot that exists in this quadrant of our z-score grid right here is going to be positive. And anything that exists over here is going to have a positive z-score for first name and positive z-score for last name. So anything over there is going to be positive. Anything over here is going to be negative, and anything over there is going to be negative. All right. And realistically, you can think of this in terms of how many dots are in each quadrant. You know, which quadrant is overwhelming the other quadrants. And we have a lot more dots whose products are going to end up being negative. I shouldn't say a lot more, but it looks like a few more dots whose products are going to be negative than what we might get with the positive there. All right. And so as we're adding these together, if we're going to have more negatives than positives, then this value up here, after adding them all together, probably going to be negative, and then we're dividing by the total number of values minus 1 to get our correlation coefficient. Now, the great thing is, rather than having to do that tedious calculation, Excel will do it for us. And the Excel command is coral for correlation. I'm going to bring it up real quick and calculate it for you, just to see if we in fact do get a negative correlation coefficient. So I just have to type in all this data. 5, 7. I got 5 minutes. We're almost there. 5, 7, 8, 5. 6, 5, 6, 10. 5, 6, 5, 6, 10. Oh, got it. 10. 10, 4, 6, 11. 10, 4, 6, 11. Why am I going so slow? 6, 7, 7, 8. 6, 7, 7, 8. 5, 7, 6, 9. 5, 7, 6, 9. 6, 8. 6, 8. All right, so I'm going to go to formulas and more functions, statistical and coral. And coral will ask you to first highlight one of the axes, and then it's going to ask you to highlight another one of the axes, and then it's going to give you a correlation coefficient. So my correlation coefficient here was negative 0.513. R in this case is negative 0.513. So it tells me that we do have a negative association. It's not strong. It's by no means not, zero association, but it's on the weaker side, probably, I would say. It's fairly weak. We would typically say something over 7 in either direction would be strong, somewhat strong, so on and so forth. But this is going to be pretty weak. All right. That would be the correlation coefficient. Any question about the correlation coefficient? I'm never going to ask you to calculate it because we have it on. Well, we have it on Excel. On a test, I would give it to you. No questions? All right, so let me finish this up. We have assumptions. Again, association. Association only works if we look at the relationship between two quantitative variables. So never would I ask you to say, is there an association between a person's first name and the number of letters in their last name? Because the first name is a person's first name. It is a categorical. Number is quantitative, that's fine. I would never ask you to give me the association between an apple and an orange because both of those are categorical variables. I would never ask you to give me the association between the number or how long it takes me to give a lecture and the color of people's shoes, because color of people's shoes is a categorical variable. It has to be two quantitative variables. All right. So conditions, number one, the condition is they have to be quantitative. Number two, when we put them into a scatter plot, it has to be a mostly or somewhat linear scatter plot. All right. The scatter plot must show some sort of linear, what it says is nearly linear form. All right. So we can't see any definitive curvature in our scatter plot. I erased the curved one. All right. And the last thing we need to do in order to do an association or make an association between these two quantitative variables is to have no outliers. Because an outlier is greatly going to influence our correlation coefficient. An outlier might be way out here, giving us a very high product that is positive, or out here giving us a very high product that is negative. And high products that are positive or negative are going to have a severe effect on the value of this correlation coefficient. So we don't want any outliers there. Oftentimes, if we saw an outlier in a scatter plot, we would probably exclude it, make a note of it, moving on. In addition, if I were to change the axes here, if I would have put first name here and last name here, first name on the Y, last name on the X, if I flip those axes, it's not going to change my correlation, all right? There is no connection between where, what is on what axes. Flipping them would still give me a correlation of negative 0.513. And what else? No units. When I give correlation, I would say negative 0.513. That's the end of the game. It's not 0.513 letters. It's not 0.513 inches. There are no units associated with that. If I were to change scales, maybe if I were taking weights and heights, weights in pounds, heights in inches. If I changed it to weights in kilograms and heights in feet, it would not change the correlation. Changing in scale would not change those values.